Now, what are the post tensioning hardware and systems that we have? And the wire we have studied in the reinforcement itself. Wire is the fundamental unit, pre-stressing wire, and for some applications even wire is used directly for pre-stressing, right. Depending upon if you want a very thin element, now I cannot put a strand, but we can put a wire. Wires again, it is available in different diameter. Usually pre-stressing strands are made with 5 mm wires, right. So, and then you make 7 wires strand, that is why we call that as a 7 wire strand, and that comes in either in 1/2 inch or a 0.6 inch diameter. So, you have a strand. So, the strand is the most commonly used pre-stressing steel, and the group of strand along with all the tendon system is called tendon, along with some anchorages and all, it is called as a tendon system. Now, in tendon you have unbonded tendon. Usually in unbonded tendon you will have grease will be packed, each individual strand will come up with a protective cover, and inside you will also have the grease packing, so that it is not going to corrode, right. And typically these are greased and encased. Then you have types of tendon, you have unbonded and bonded that we talked about, and this is a bonded tendon. For example, this is a flat 5 strand tendon. This way, you see it is a very flat tendon. This is used for slab application, right, because the thickness is very less, right. So, this in between, then what we do is we grout it, right. So, encased and then they are actually grouted. Then anchorage device, you see here in a duct, typically you will have this kind of an anchorage device at the end, you will have anchorage block, then you will have the wedge grips, then you also will have something called cap, anchorage caps that will be there, and then you have anchorage guide. So, this is like a something like a trumpet, that it goes out, that is called anchorage guide. Then after stretching you put the grout through this, that is a grout vent. So, you have this entire system is the anchorage device. The entire system we call that as a tendon with anchorage, right. So, now again what are the unbonded systems? Again, this is an example of again a figure with unbonded system. You see, whenever you have unbonded system, code also mandates you to put some normal non-pre-stressed steel, right. So, you have to satisfy, you have to also put this non-pre-stressed steel, that what you see, right. All these things are non-pre-stressed steel, along with this green color thing what you see, the green colors are actually elements of the unbonded tendons, right. So, you can see the tendons, they remain functionally separated from the concrete along their length for the entire life of the structure. There is no physical contact of the strand inside the duct and the surrounding concrete, right. Now, here the pre-stressing force is transferred to the concrete only by anchorage or deviators. Okay. Deviators are the ones that helps to change the profile of the tendon, right. Now, in bonded tendon, as the name says, the tendons are attached to the encasing concrete along their length and follow the deformation of the concrete, right. So, the compatibility is always there, right. So, the tendon which pre-stressing steel is bonded to the concrete and it is permanently prevented from moving relative to the concrete. But in case of unbonded tendons, locally you may have some movement that can happen relative to the surrounding concrete, but overall the deformation will be same between the concrete and the unbonded tendon. But in a bonded tendon, each location you satisfy strain compatibility. So, you are preventing the relative movement of the tendon with the concrete. Right. Now, what are the corrosion protections? Different systems evolved over a period of time, particularly North America and Europe. Late in 1950s up to 70s, we had something called paper wrap system. The cables were, the strands were just wrapped with paper, but then it is not moisture proof. So, it created corrosion issues over a period of time. Then plastic sheathing came from 1960s, even some of the applications we are using plastic sheathed strands. Then you have encapsulated system from 1985 onwards, it is available in North America, and in India also nowadays we are using encapsulated system. And we have the most advanced system is an electrically isolated tendons. That means absolutely the tendon will not have any contact, right, any contact, always it is covered with some plastic sheathing, right. So, that is a most advanced one. These are some of the pictures. You have a strand and then it is covered by paper, is the oldest system. Then we have a sheathing, a cover that is there. The sheath is usually, while you make, the sheathing is also extruded along with the strand, and then you have sheathing. On top of that, you will have one more plastic tube, and then the surroundings are also the anchor blocks are also grease filled with plastic cup. Then you have plastic coated anchorage as well. So, these are all some of the systems that has evolved over a period of time. So, the current ones are quite good from corrosion resistance point of view, but again grouting has to be done in a proper way. Otherwise, if the grouting is not done properly, then again you will have corrosion issues. That is a separate topic. You can look at the specialized literature on what are the guidelines for grouting. Okay, some examples. You can see this is one of the biogas tank in Punjab in India, and you can see this entire tank was actually, the walls of these tanks were actually post tension, and along with that you have these long girders, they were also post tension. And then this is another applications of a flat slab. Again, here it is actually a flat plate. You can see here the column is directly connected to the slab. So, this is a E-rod steel office in Tirupur in Tamil Nadu in India, and the span is about 33 feet, and you can see this kind of a very elegant structure can be made using post tension technique. Now, moving forward, again this is some of the pictures of a flat slab construction. As you can see here there is absolutely using bonded tendon. So, these are bonded system. That is the reason you do not find other non-prestressed system. There are no non-prestressed rebars because the cable itself is a bonded system. So, it is one way of doing it, but the code, depending upon which code they are following, they will always mandate some minimum reinforcement by combining both the PT cable and the non-prestressed. So, that reinforcement limit you have to anyway satisfy, right. So, this is another example where you have a flat slab construction using unbonded tendon, but here in this example you see you have always some reinforcements are kept, okay, at critical locations. So, the code, according to the code what you are following, always you have to meet the minimum requirements of steel. Now, so what are the design considerations for the PT slab? So, the selection of a structural system, as you can see, the column supported slab construction, typically we use strip method for reinforcement layout, okay, depending upon whether you are going to transfer the load as a one way or two way. So, for example, in a two way system, what we are going to do is the slab is designed and reinforced for 100% in one direction, and then again that means I am designing the load to be transferred in either orthogonal directions 100% in each of these orthogonal direction, right. So, whenever the ratio of the longer to the shorter side of the slab is at least equal to 2, it is called as one way slab. So, when the aspect ratio of the slab to longer side to shorter side becomes more than 2, then the slab is going to bend predominantly in one direction, it is called as a one way slab, right. And under the action of loads, I can see one way slab deflects in shorter direction only, because that is the main span, that is where the curvature is going to be there in a cylindrical form. So, the primary reinforcement is usually placed only in the shorter direction. Now, this is again a guideline that we can follow. For example, depending upon your aspect ratio, if I take a longer dimension as B and shorter direction as A, if I divide that ratio, if that ratio is greater than 2, B by A is greater than 2, then it is a one way system, then you design it as a one way slab. If it is going to be between 1.4A is less than B is less than 2A, that means the ratios between 1.4 and B by A is between 1.4 and 2, then it is not exactly, it is getting into a two way system, then I can go for a slab band reinforcement, right. So, that will lead to more economical system, but if B is less than 1.4A, then it is a very clear two way slab system, then I have to design that as a proper two way slab system. So, if only when the ratio is between 1.4 and 2, then I can consider slab band system, right. So, structural systems again for flat slabs typically are used when your longer side to shorter side is less than 1.4, and flat slabs with bands we go for when the ratio is between 2 and 1.4, and beam with one-way slab system is used when your aspect ratio, that is the longer side to shorter side, is more than 2, because it is going to predominantly, the slab is now going to predominantly bend only in the shorter direction like this, right. So, this the entire the slab, now I can consider this as a one-way continuous slab, right, that we have studied in the continuous system, how to design a beam, continuous beam. See, similarly, slab is also going to act like a beam as a one-way continuous system. We take 1 meter wide strips and then we design for it, right. Okay, this is what one-way system. So, the loads acting vertically downwards on the beam or slab, and then your bending moment and shear will be resisted only along one axis, depending upon the span direction that you have, that you can see, which are indicated by the arrows and moments. But in two-way systems, you can see that a two-way system transfers the loads in both perpendicular directions in a two-way slab or a grid structure. You can see the moments. The bending moment and reactions occur in both directions, and it allows the load distribution over a larger area. So, that is why two-way systems are highly redundant, and it can develop more number of load paths. So, typically strength is not an issue at all when you have a two-way system. It is a deflection, and for flat plate systems, maybe punching shear will start governing the behavior, but strength is typically, people have tested some two-way slab systems, though it was designed for let us say X loads, when it was failing, they were getting as high as 10 times the design load. So, strength is not at all an issue when you have a two-way system, but it will be governed by other considerations like punching shear or deflections. Mostly it is the deflections when you have beam supported slabs. If it is a flat plate, depending upon the loading and span, either deflection or punching shear can govern the design. Now, when do I go for post tensioning, right? For example, same for a particular span, I can do with RC or I can do with a PT, right? Now, you see here for spans higher than 7 meters. So, in the left what we have is a relative cost per square meter including the supporting columns, right. So, the lesser it is, then more cheaper the particular option. So, for example, you see here the break even point for between RC and PT is at 7 meter. That means for spans anything more than 7 meter for a flat plate, going for a post tensioning will become economical, right. So, that is the reason typically up to 7 meter we do it with RC only. Anything more than 7 meter spans, then I can design that as a post tension concrete, right. Similarly, for one-way slab with a slab band, you can see here that number is also about 6.25. So, anything more than 6.25, then it becomes very attractive to go for post tension concrete. The longer the span is, more economical is the option for going for post tension, right. So, now when it comes to two-way systems, I can also orient the PT cables in different ways. And what are the common ways with which people orient the PT cables? So, uniform load balancing in post tension slabs is achieved by concentrating the tendons in column strips. Basically, in other way, we are actually, though this reinforcement is inside the slab, we are actually forming a pre-stress beam along the column line, right. So, this kind of banded PT cable that we are creating, right. So, in a way, I am creating a hidden, though it is only slab, even in a flat plate system, if I orient the cables like this, I am actually running a hidden beam which is stiffer in the along the column lines. That is what I am doing. So, this is 100% banded through columns. I put only PT cables in the close to the column supports in both X and Y direction, right. Now, in this case, then whatever that additional reinforcement that is from strength point of view I need, I am going to put it with a normal non-pre-stressed steel, right. Now, I can also do another way. One side I go for a banded system, right, On the other side, I go for a uniform layout of the tendons. So, these are basically layout of the tendons. Okay. So, tendon distribution is what we are talking about, right. So, this is also can be done. So, but actually the layout whatever that we are choosing should reflect the expected moment distribution in the slab with recommended concentrations of 65 to 75% in column strips and the rest in the middle strip. So, if you look at it in a two-way slab system, the column strip along the strip is where it will take the stiffer region will attract always the higher forces. So, the more bending moment will be there in the column strip regions. So, that is the reason you need to even PT cables, you need to put more PT cables in the column strip region and then some nominal amount can be put in the middle strip region. Middle strip is the region between the column strips, right. So, we know that, right. So, typically a recommended layout is 75% you put in the column strip and remaining 25% you put it in a uniform way in the middle strip region. So, that is the recommended layout. So, this is one way of doing it. For example, you see here this is middle strip, this is column strip and this is a middle strip. So, basically what we do is we will study more about how do we split the slab into column strip, middle strip in the equivalent frame chapter in the third part of this module, where we will spend more time on how to discretize this. But what you can see is the region that are away from the column line region is called as a middle strip. Okay. So, then what we do is we try to put 75% of the banded tendons through the column line or column strip in both the directions and 25% of the middle strip in both the directions, right. So, this is this is what we do. For example, you see here this is in this case, then you can see this is in the LY direction, okay, in the other direction. So, you see here we do it. Now, I am showing the reinforcement in the other direction. So, this is 75% banded to the columns in one direction and 25% along the LY direction. So, this is what we are trying to do. So, we are trying to put uniform, so the layout like this. So, in that way 75-25 is a very good layout that what we can do to get a very nice economical distribution and design for the PT slab. Okay. Now, why do we do that? When you do that, a more uniform load balancing. So, we know what is the load balancing. So, as we have seen, the cable profile is creating horizontal component that is going to squeeze the concrete and putting it in compression. The vertical component is going to nullify the external load. Now, when I do this 75%, 25%, I get a more uniform load balancing on the entire slab region. So, that means I am going to balance the external load in a quite effective and efficient manner, right. So, the distribution when I do that more closely resembles the distributions of the moments in the slabs. The concentration of the tendons in immediate column region increases the punching shear strength also. As you know, the shear strength is always function of the amount of steel that is there. If you can see, recollect tau c expression that what we have in our code also is function of the amount of tension reinforcement that you have. So, if you have more reinforcement in the column strip region, the tau c also goes up, right. So, in that way it is also indirectly helping you in reducing the probability for the punching shear failure, or I should say punching shear strength is increased. The tendon concentration in the region through column increases the moment transfer also at the slab column connection. That also helps in better transfer of the moment transfer at the slab column connections. Now, so this is with respect to two-way slab.